Cool. Thank you very much for the nice introduction. Let's go back to full screen. So the title of my talk now is the title of a recent publication. What is it going to be about? I will first introduce the Bayesian brain hypothesis as a unifying theory of brain functioning. This is an autobiographical part of my talk. Then I will also describe how in two recent studies we applied these hypotheses to study anorexia nervosa. So it all started for me in high school when I had a lecture, which I believe you all had, where they explained to me that there are 4 fundamental forces in nature. And this means that these forces are in principle able to describe all the phenomena we see. And I guess you're familiar with gravity and electromagnetism. The other 2 forces are a bit more enigmatic, but at least the strong interaction should be well motivated as the force that keeps the neutron and protons bound in the atomic nuclei. And this idea was very interesting to me. So when I went to university, I studied particle physics, and I discovered in last year that actually the electromagnetic and the weak force are the same force. They are just the manifestation of the same force that's called electroweak. And it's the foundation of the standard model, which was discovered in the 60s. And then there was also this other strong force, which has a mathematical formulation very similar to these other 2. So already in the 70s, people started to say, hey, but aren't these 3 forces not exactly the same force? And this idea is called current unified theory. And there are many different models now. And I worked in my thesis on a model that could unify these 3 forces and explain the neutrino masses. In the 90s, or even before, actually, there started to be the idea of a grand unified theory that would unify all the forces in nature. And pretty surprisingly, gravity is the most trivial of the forces for all of us, but it's the most difficult to unify here. But to make a long story short, what was very interesting for me is this idea that you can have a theory or you wish to have a theory that can explain all the phenomena observed. And when I switched to psychiatry nearly 8 years ago, I found a very different environment. I was in a lab where the main research topic was anorexia nervosa, and still is. And there were other scientists, and each was working on a task that would try to explain some particular aspect of anorexia nervosa. And each of these tasks there was kind of a theory to explain what was going to happen in the task. And I think this is actually how big theory emerged, like from different competing theories. But my biggest question was, okay, but assuming that I'm able to really find convincing support for one of these theories, is this theory also going to tell me something about other psychiatric disorders? And therefore, I was very happy when I first stumbled in the idea of Bayesian. Essentially, this hypothesis says that the brain is a machine that continuously tries to infer the causes of the sensations. And to do that, he has a running model of the world, which is called a generative model. And the main motivation for this hypothesis comes actually from cybernetics. There is a theorem there that says that every good regulator of a system must be a model of the system. So a regulator is simply a device which tries to keep some quantity constant. So it could be the speed of a car, but for biological system, it might be some temperature, pressure, or some other chemical equilibrium constant. And this, importantly, outside of thermal equilibrium. So we're trying to keep a body temperature of 37 degrees when outside the temperature is 20. And if you accept this motivation, then it's pretty clear that the biological system should be trying to use bias inference, because this has been proved to be the optimal ways to use information. I think you're all familiar with the Bayes theorem, but the way we are going to read the Bayes theorem, which is equivalent to Bayes inference, is this way. So in this equation, we are going to see that B are essentially the sensations, and A are the hidden causes of these sensations. And suppose that, for example, you are trying to cross a street and you see a car approaching. So the images of this car approaching are somehow the sensations B. And what you would like to guess is, or infer, is like the speed and the position of the car, and finally the time at which the car is going to be in the same position as you. So to decide if it is the right time to cross the road. And of course, to give an answer to this, it's not enough to just observe the car, but to have a more precise estimate of this, we typically rely on priors, right? So we see a car, and if we are on the motorway, well, okay, we're trying to cross the motorway. It's not very good idea, but we are assuming, okay, the speed can be 100 kilometers per hour or even more. And if we are in the city, we're typically assuming a much smaller speed. And based on this prior and the information that we get using our eyes, then we can get an estimate of so the posterior probability of the posterior of which tell us the distribution of the velocity and the time and the position of the car. What is important here is that the final position will depend on our prior beliefs. So, and these prior beliefs are based on our past experiences. Now, keep into account that all this inference process is in this Bayesian Brain hypothesis, a continuous process. So we continuously have priors that are going to be updated by the observation using this Bayes theorem to compute posteriors. And then the posteriors become the priors. And this process that happens continuously every second is actually a process that, if you look at what exactly this equation means, well, it involves distribution probabilities, and therefore all these computing this ratio and computing the final distribution probability for the variables that interest us, like the velocity of the car, is an unfeasible combination of integrals. So there have been, people have realized, okay, the brain cannot be really doing a precise Bayesian inference, but probably it relies on some approximation. And as I will present later, you can prove that under some approximation, Bayesian inference really looks a bit like reinforcement learning. So the rules for updating the priors are essentially based on some prediction errors, which are essentially the difference between the prediction of the sensations that our generative model is doing minus, the sensation that we are really observing minus the sensation that we are really predicting. So this model is very opposite to the idea of tabula rasa, right? So when we are looking at an object, we are not just waiting for the photons to reach the retina of our eyes to have an idea of what the object looks like, but we already have a model of what that object is, and we are basically just comparing our prediction with the observation. And this is not just theoretical ideas, but there have been some experimental evidence that there are prediction error signals in the brain. And one example is emission paradigms. In these paradigms, essentially, you have like a very repetitive beep so there is a beep every second for say 50 seconds, and then suddenly there is no beep. And you would observe that there are some signals in the same brain areas that usually activate when some noise or some beep is heard. So how do we use this for psychiatry or for psychopathological behavior? We make use essentially of the complete class theorem that says that given a behavior, no matter how atypical that is, there is always a set of prior beliefs that we can use such that we can explain that behavior as being based of optimal Bayes inference. So that is pretty cool because it sets like a roadmap for psychiatry for all of it, right? So it says we have some disorder or in general some atypical behavior and we want to explain it. We just have to find the priors that would make this behavior Bayes optimal. And then we have to admit, so the Bayesian brain hypothesis doesn't do everything for us. We have to find the biological substrates of these priors. But there are some publications that say that nevertheless, this hypothesis still puts some constraint of how this biological substrate has to look like. To give you an example of what kind of conclusions you can reach using this hypothesis, I will bring up the example of autism and schizophrenia. There are findings that suggest that in autism, the prior for the volatility is increased. What is volatility? Volatility is, for an observer, is the estimate of how fast and how much is the environment going to change. And if my prior over the volatility is increased, then I would rely on sensory data more than a neurotypical individual. In schizophrenia, what's happening is kind of the opposite, and there are findings here that suggest that hallucination might be explained by over-precise prior beliefs. This brings to an under-reliance on sensory data. So how did we apply in our group this idea to anorexia nervosa? Well, so first of all, a brief introduction. I guess it's well known in the general public that anorexia nervosa is associated with a relentless pursuit of thinness. It has a much higher prevalence in women and a typical onset in adolescence. And contrary to what is commonly believed, it's not just a product of our Instagram society, but has a very high irritability rates. There is no specific, no pharmacological treatment specific for anorexia nervosa, and this might be one of the reasons why it has very bad outcomes. It has the highest mortality rate of all psychiatric disorders, very high relapse, and a lot of individuals develop a chronic form of anorexia nervosa, and even if they don't, there are often long-term consequences. In this study, what we are going to investigate is whether the personality traits that are often observed in individuals with anorexia nervosa might reflect some risk factors. And I will concentrate on pessimism, perfectionism, and harm avoidance. To do so, we use a probabilistic reversal learning task that was done during fMRI. In this task, participants have to choose between two symbols. One is the so-called correct one, and it gives a reward 80% of the time and punishment 20% of the times, and the other symbol is wrong. And this means that the reward contingencies are simply reversed. Therefore, the participants to successfully complete this task, to maximize their win, have to be able to disentangle noise from signal. Also, to make the task more difficult, contingencies would reverse, which means that after the participant choose for 4 times the correct symbol, there was a chance that the contingency would reverse, so that the correct symbol became the wrong symbol and vice versa. Therefore, participants had to be flexible to change their beliefs about the reward contingencies. When we started the studies, there were already various reports of increased punishment sensitivity in anorexia nervosa that were based on self-report. And therefore, our hypothesis was generally that the decision-making in anorexia nervosa would be more affected by punishment, by punishing symbols, or in this case, monetary loss, relative to healthy controls. And based on neuroscientific findings, the general population, we also expected that the traces of these alterations in learning would lie in the posterior medial frontal cortex, which is a region that is broadly, roughly the union of the dorsal anterior cingulate cortex and the supplementary motor area. We actually built this mask by intersecting these 2 regions with the neurosynth forward map for the word learning. As I mentioned at the beginning, we had 2 studies. In the first study, we compared acutely underweight participants with pairwise age-matched and healthy controls. And in the second study, we compared former patients that were fully weight recovered with healthy controls. And this is a bit summary of demographic and clinical measures on our samples. As you can see, well, BMI was very much reduced in the upper end group, the group of acutely underweight patients, and it was normal in the group of RECA-N, namely recovered former patients with anorexia nervosa. And these last variables are assessing eating disorder symbols, EDI, and BDI is assessing depressive symptoms, and GTCI is assessing many things, but we just consider the scale of harm avoidance. As you can see, the acute have strong symptoms, and recovered participants not so much, but there are still some differences in EDI and PDI. So how did we model the behavior and the fMRI data? Essentially, we assumed that participant would first infer the expected reward of each option using a so-called perceptual model. And then, based on these, on the results of this perceptual model, they would make a decision. And therefore, we had like an observational model that, based on the difference in expected value or expected reward, would give the probability that the one or the other option are chosen. So as you can see, many curves for this observational model are possible, of course. There are some general constraints that we expect, for example, that the probability of choosing square is increased when the expected value of square is much bigger than the expected value for circle. However, all these models will have some parameters that are specific for each individual. And therefore, we would first select some plausible models for the perceptual model and observational model. For each model and each participant, we would find the best parameters using maximum mass posteriori bias estimates. And then we would use Bayesian model selection to guess which model was used by each group. Specifically, in this study, we just had one observational model, which is the softmax. I guess you know this model. What is important here is that it has one free parameter, this beta. The higher the beta, the higher the probability that the option with the higher expected value is chosen. And for the perceptual models, we compare the three models. The first one is the simplest reinforcement learning model. The expected value at each trial depends on the expected value in the previous trial, plus some free parameter that is called learning rate times the prediction error, which is essentially the received reward or punishment minus the expected reward. We also had a Scholar-Warner model with the trial-dependent learning rate, where here the trial dependence in the learning rate is computed, I would say, heuristically based on smoothness and some other reasonable constraints. And finally, we had the hierarchical Gaussian filter, which is a model that is based on the Bayesian Brain hypothesis. It's saying that the observer performs approximate Bayesian inference. It can be represented by this small plot, where actually the red part is the observational model, so the softmax. And as you can see here, hexagons are variables that have a time dependence, and the blue circles represent parameters that are time independent, but specific for each individual. And here it looks very complicated, but essentially x2 is like, it represents the expected value, and x1 as well. The only difference is that x2 is like so-called tendency towards rewards, because it's a variable that goes from minus infinite to plus infinite, and x1 is a transformation of this variable so that it has values between 0 and 1. And as you can see, it's the generative model underlying this hierarchical Gaussian filter is the Gaussian random walk. So the expected value at trial k depends on the expected value at trial k minus 1, plus a jump, a step, whose amplitude depends on the on x3, which is the time-dependent part of volatility, and combined with these two parameters, which all in all make the volatility of the environment. All this could be very, this model could be very complicated to invert, namely based on the response of the individuals on the input they got. Inverting the model would mean to compute each of these trial-dependent variables and also the individual-specific learning parameters. However, under some approximation, what the Mattis et al. Showed is that we can essentially compute the evolution equations. I mean, we can compute some update equations for the expectation value for the learning rate and the prediction error, using some equations that are very similar to reinforcement learning models. What you would get is a trial-dependent learning rate, and you would get precisely a dependence on time that is written in terms of the volatility, the precision of the current state, and you would observe that you expect to have the participants are expected to estimate a higher volatility in their environment, are going to have a higher learning rate when they estimate the environment to be more volatile. And also the learning rate depends on the precision of the current state. The higher the precision, the knowledge of the current state is, the lower the learning rate is going to be. And since Bayesian model selection revealed that the hierarchical Gaussian filter was the best model for all groups, ACA and RECA and healthy controls taken separately and together, this is the one that we use in the following analysis. And mainly what did we analyze? So we compared the model parameters, so beta, theta, and omega between groups. And however, I found that this comparison was not really ideal to test our initial hypothesis, because these model parameters do not differentiate between punishments and rewards. And then we used linear mixed effect models for the time-dependent parameters and for the reaction times, having as factors group, response, and feedback. Response is whether the response chosen by the participants was correct or wrong, and the feedback was reward or punishment feedback. And these time-dependent parameters we also use that as parametric modulators to predict the bold signal. Specifically, there are some, based on previous publications, we expected that during the learning phase, which I will explain later what it is, the bold signal in the posterior medial frontal cortex will be proportional to the learning rate. We expected that the signal in the ventromedial frontal cortex would be proportional to the expected value or expected reward. And the signal in the ventral striatum would be proportional to the prediction. Specifically, we connected the decision phase to the expected value, and we defined it to occur 1 second before, to start 1 second before button press and to end with button press. And we called learning phase the interval starting with feedback presentation and ending 1 second after. In the fMRI model, we also had some other reasons, regressors related to stimulus appearance and also movement, motion, and so on. So these are the results. So as I said, we had 2 studies. In both studies, we found that a group feedback interaction for the learning rate was significant. When we computed post-hoc t-test in the first study, we discovered that, okay, so first of all, it's important to realize that we always expect that the learning rate after punishments is increased compared to the learning rate after reward, because so punishments are typically signaling that something is wrong in our model of the world and that we have to change it, right? What we found when we look at postdoc tests is that in acute participants, the learning rate after punishment was increased compared to healthy control, which was in line with many findings of increased punishment sensitivity in anorexia nervosa. However, when we look at the RICA-N data, at the data on former patients, we didn't find a significant difference in the learning rate after punishment. But what could explain the interaction was that the difference in learning rate between punishment, learning rate after punishment minus learning rate after reward was increased in both anorexia nervosa groups. And the effect sizes were also similar. And we found that this difference was not related to clinical symptoms like EDI, BMI, former patients. In the other trial-dependent parameter, we didn't find any effect or interactions. So then we looked at the fMRI data. We found, as expected, that during the learning phase, there is an area in the posterior medial frontal cortex where the ball signal is proportional to the learning rate. This in both studies. At the time of the first study, we said, okay, I mean, the learning rate after punishment is increased in AKN, and bold activation in this region in the posterior medial frontal cortex is proportional to the learning rate. So we also expect that if we remove all parametric modulators, the activation in the PMFC will be increased after punishment in acute patients. And this is indeed what we found. Here you see the blob where this is the case, and here you can see that this blob really overlaps with the region where there is an activation proportional to the learning rate. In recovered former patients, we didn't have that the learning rate after punishment was increased. However, we still found this fMRI signal that there is an increased activation after punishment in the posterior medial frontal cortex. And all these regions overlap pretty nicely. So the region where there is an activation proportional to the learning rate, a region where AKN have increased activation, and the region where RICA-N have increased activation. And these findings were also there in a model where we regressed out age or BMI. Yeah, and of course, so these are actually some sanity checks. We also found the expected fMRI activation in the ventral stratum, while not so well, proportional to the prediction errors, and in the ventral medial prefrontal cortex, proportional to the expected reward. This brings me to my conclusions. So what we have found, I mean, the way we interpreted our findings is that both acute patients and former patients attribute more meaning to punishment. So when they receive stimuli with a negative valence, they are more prone to update their beliefs compared to healthy controls. So they attribute more meaning to punishment, but also at the same time less to reward. We have found signs that this persists through recovery and doesn't correlate with clinical variables like BMI, and therefore we think it might be trait of anorexia nervosa, with some caveats we'll detail later. In the last studies, we also realized that this cognitive style of giving a lot of weight to negative stimuli and at the same time less weight to rewarding signals could promote low mood. And we tested this using a model by Neve et al. That sees mood as a representation of momentum in some reinforcement learning setting. There are, of course, a lot of limitations. You might think that a very important one is a sample size, and surely it is. Nevertheless, I was quite surprised that we could replicate our findings in a completely independent sample, I mean, between AKN and REKN. Surely enough, we should be careful interpreting these findings as trait markers, as they could also be scar, I mean, long-term consequences of anorexia nervosa. It is, however, quite difficult to overcome this limitation in future studies because, I mean, surely one could do prospective study from morbid individuals, but since anorexia nervosa is quite a condition, one would need thousands of participants to get 30 or 40 individuals with an N. Another alternative that has been suggested in the last years is to use studies in which there are monozygotic twins, one affected and the other not. Another limitation is that our sample of recovered still presented some signs of depressive and eating disorder symptoms. So people might object whether the recovery was complete. And also another problem is that we finally conclude that both groups, I mean, acute, recovered patients and healthy control use the same computational strategy, and there are differences only in the parameters, but of course, we just tested 3 models, and it's not clear what would happen if we would test more models. I have also some more general conclusion. I think computational modeling is quite interesting and useful, generally also to build unified theories. It allows to formulate hypotheses in terms of computations that the brain has to do to perform given choices or behaviors. So it allows to formulate these hypotheses in objective terms, and it also helps to overcome the difficulty of, I mean, of observed individuals to sometimes verbalize their experiences they are going through. Certainly, there are other objective measures like total win or correct answers, but in these cases, the information contained in these measures is much less and doesn't concern the processes that bring to a given decision. And it also allowed us to connect the alterations that we found at the behavioral level to possible neural mechanisms. So this is all I wanted to tell you. So I thank you for your attention, and also would like to thank